All right, welcome everyone. So we have 16 participants. We're going to wait a bit further until we hit, let's say, 20 participants or so. And today, after the nonstop weeks of, let's say, deriving something very complicated and sometimes slightly counterintuitive, today it's going to be much more relaxed. So we don't have to worry too much about covering all the content. So we'll wait another 2 minutes before we have enough people joining us. Okay, we have already 20 participants. And as usual, please mute yourself and then turn off your video. And if you have any questions, please do type it in the Zoom group chat. And then once a while, I'm going to look into the chat to ensure that I answer all the questions you have. As I said earlier, today's lecture is finally, after all those weeks of grueling derivations and sometimes counterintuitive results we received, today's lecture is going to be so much more relaxed. In a sense that everything that we talked about today is going to be very intuitive and then does not involve too much of the mathematical derivations that we have done so far. Meanwhile, let me just... All right, so we have 23 participants. Let's wait one more minute so that we hit 25 participants. Okay, 24, just one more student to join. Oops. Maybe 24 is the maximum we can get. Okay, we have 25th, let's say, participant who has just joined. So we're going to start today's lecture. So far, until now, what we have looked at or what we have assumed is the availability of a set of training instances. What it means is that when we talk about the data, so we use the D often to indicate a set of training instances or a set of examples in general. What we assumed was that we have the inputs that are presented as vectors. Oops, we have been using N here. And then what we assumed, although we didn't really specify it, is that each and every one of these input vectors, so x1, x2, and all the way to xn, are independently drawn from the underlying distribution. What it means is that the probability of x1, x2, all the way to xn, so we can think of all these variables as random variables, as we talked about, could be rewritten as the product of the probability of each and every one of them. And then what we assumed further was that all these probabilities from which x1, x2, and xn follow were the same thing. So all these probability distributions are the same. And then this is where some confusions arose, rightfully so, on campus wire, that how is it that this P is used over and over while the input to this P change from every application? Doesn't the application of x1 here, or the writing down x1 here, imply that this P is a different P function from the P when we wrote down the x2? That's perfectly true. So the P here, the letter alphabet P in this mathematical context is one of the most overloaded symbol that we use. And then when we say P here as a symbol for function, what it means is that this indicates either the probability mass or the probability density of the variable that has been passed. What it means is that we have to look at what is the variable that is being passed into this function indicated by P in order to tell what is the specific thing that is being returned by this function. And then what it means is that when I write down as the P of x1 times P of x2 times all the way to the P of xn, all these P's here may indicate different functions. They might return probability mass, they might return probability density, who knows? It's going to be based on what is being passed in. So here, the first P of x1 indicates that this is the probability of x1, the random variable x1. P of x2 is going to the probability of the second random variable, or the random variable that corresponds to the second observation. And then here is going to be the probability, either mass or density, of the nth random variable, or the random variable that corresponds to the nth input vector xn. But then one thing that we assumed, if you remember from the Bayesian linear regression, and even from the very first lecture, is that all these input vectors are sampled from the same distribution. So in this specific case, under the context that we talked about, they are all same. What this means is that we have two conditions here. So here, the condition was that the independence. So that is, each and every input vector, x1, x2, all the way to xn, are independent from each other. So when we generate, or when we sample the second input vector, x2, from this distribution, we don't really care what the x1 was, nor xn was, nor any other input vector was. So that's the independence. And then the second condition is that the identical. Oops. So what is this identical means is that as I said, all the distributions, so there is only a single distribution from which we sample x1, x2, and xn, every single one of them. And then when we combine these two conditions, we call this condition IID. So it's independent and identically distributed. So independent, identically distributed. So this is a very classical assumption that we make when we look at the data set in a traditional machine learning. And then, that just continues to be the case. However, as we start applying machine learning techniques and algorithms to more and more sophisticated, or the more and more real problems, what we end up running into, or what we end up with, is that the data set may not consist of the examples that are independent and identically distributed. So what does that mean? Is that in this specific case, you can think of it as if the samples satisfy this IID condition, there is no correlation across all these examples. However, that may not be true in general, right? And then what is the most general way to put or to describe a data where IID condition is not satisfied? That is, that the data could be given to us as graphs. And then what is this graphs? Let's talk about this graphs. What is graph? So we're going to use the letter G to identify, or the character is this graph. Graph consists of V and E, where the V stands for vertex, and then E stands for edge. So, and then vertex, or sometimes people call it node, all the same thing. And then you can imagine any kind of graph that that you can imagine, right? So you can think about the social networks. That is one gigantic graph that we have. And then every node in a social network corresponds to individual user. And then edge is going to tell you whether a pair of users in this social network are friends with each other. And that's going to be a graph. Now, what else can you think about? You can think about, for instance, a molecule. So molecules could be represented as graphs. So each molecule consists of the atoms, and each and every pair of atoms can be characterized by the type of the bond they have. What else can you think about? There are so many things. And in fact, you realize that the graph is one of the most generic representation because, for instance, sequences or trees, they are all special types or the special cases of graphs. And then if you think about the trees, you can think about the, for instance, family tree. And that's also a graph. In the family tree, every node corresponds to your relatives and yourself. And then the edge corresponds to whether corresponds to the relationship between you and your parents. And then based on that, you can build a graph, and then that's going to be presented to you as a data instead of having a set of IID samples. So in the case of the IID samples, each and every data point should be independent and identically distributed. And then in the cases that we just talked about, this IID assumption doesn't really hold. In the case of the social network, of course, users may be identically distributed in a sense that there is a one single distribution that is going to be very complicated that describes the entire population, and then we sample from them, but they are not independent because we're going to look at only the samples that are related to each other. So who uses, for instance, Facebook in the world? You only use Facebook if you have your friends already on Facebook or your friends or family so that you can connect with them. Meaning that the fact that I'm going to start using Facebook, Instagram, or whatnot does not happen independently of all the other users, but that happens because I am inclined to be friends or in contact, in touch with other friends of mine who are already in Facebook. So what it means is that it's not going to be independent. So these independent and identically distributed, these IID assumptions may not hold. And in particular, in the case of the unsupervised learning, unsupervised learning can be very useful for graph learning. So what do I mean by graph learning? What graph does is that this graph is going to tell us about the structure behind the large database. So we're going to stick to this social network example because that actually tells us a lot about it. So in this vertex set V, we are going to have number of vertices. So each and every one of these can be considered as the number of users in this social network. And then each and every user is going to be characterized by their properties. So in my case, in my Facebook social network, who would I be? I'll be a male, works at NYU, lives in New York City, and then all those properties characterize myself. If you're on Instagram, then similar thing. And then even in a molecule, you get the similar thing, is that each atom is going to be described by its own properties. So these we can think of having, let's say, d-dimensional vectors. And then now we have edge set. And this edge set consists of edge between a pair of instances. And then again, each and every edge can be represented in a way that characterizes what kind of relationship between two nodes have. And in our case, we're going to simply say each edge is characterized by its weight. So it's going to be just a one-dimensional real value. Of course, we can always extend it into multi-dimensional real values. We're going to talk about that briefly near the end of the course, but we're going to stick to the case where each edge has a strength. So in the case of the social network in Facebook, the strength is going to be either 0 or 1. Either you and your friend are friends to each other on Facebook or not. However, that's not necessarily the only way to characterize this. So if you have been messaging your friend more often than other friends, maybe we should consider the bond between you and the specific friend to be higher or stronger than the bond between you and another friend of yours that you never really talk to. So we're going to simply say this is more like the spectrum rather than binary value. So we're going to allow that by having a real valued strength. So we have a characterization of each node, that's RD, and then we have the strength. Now, what we are going to assume here for now is that this characterization of each node is unknown. Which is often the case. So for instance, what would be a case in which we have no idea about the node characteristics, but we only know the strength or strength of the edges? Of course, looking at the social net is one way to go, right? But of course, in social net, you do have a lot of information about yourself as well as your friends. Now, in the case of the molecules, same thing. You know a lot about each individual atom without having to resort into in which kind of context, molecular context, the atom appears. How about airports? So there are a lot of airports in the world, but when you think about each and every airport, it's very unclear what is the right way to characterize them so that each and every airport is going to be unique and the representation is useful for us. Maybe the number of, maybe their locations, but does the location tell us everything about the airports? That's not necessarily true. For instance, in New York area, there are at least 4 to 5 airports, and then all those airports, although they are located very close to each other, are very different. So perhaps we should look at the size of each of those airports. But then the size alone doesn't really tell us about the airport, because what is the definition of the size of an airport? Is it the actual length, or is it just the number of the people that uses it, right? So in other words, there are a lot of cases in which we don't know what is the right way to characterize a node, but we know the edges or the graph structure. In the case of this airports data or the airports, the connectivity, that is, whether there is a direct flight from one airport to another, could actually tell us, and how many such flights there are each week or each day could tell us a lot about the graph structure of all those airports. So before we continue, there's one question from Annan. What is the meaning of the index of an edge? Does E11 mean the strength of vertex 1 with itself? Yes, that's true. So here, when I look at the edge, so let me rewrite this into the form that is clearer. So if I write it as the Eij, so where the I can go from 1 to n, and then j can go from 1 to n, what this tells us is what is the strength of the edge connecting the ith and jth nodes. So this is how we are going to write the edge strength. So E11 is going to be the edge strength of its own. So we're not assuming anything about whether there could be or could not be a self-connecting edge. And then that really doesn't matter that much in this case, because what we're saying is that if we're going to assign the strength to each of the edge, if the strength is 0, then that's effectively going to tell us that those two nodes that are connected by this edge with the strength 0 are not effectively connected. So we are given this graph, but what each and every node is unknown. So just imagine an airport data where you have a list of all those airports. You don't really know exactly how to characterize each and every one of those airports. However, you know how many direct flights there are every week. Let's go for every week between each and every pair. A lot of them are not going to have any direct flight with each other. However, some of them are going to be, and eventually almost all these airports are connected with each other, not directly, but indirectly via other airports. And then that's, you can guess as true. So we have this kind of graph, and then our goal now is to figure out what this unknown vector that characterizes each node is. So how will we do this? What we are going to do is we're going to resort to this matrix factorization that we have been using so far. So what we're going to introduce first is we're going to introduce something called adjacency matrix A. And then this A is going to be R n by n. So this adjacency matrix is just like an edge matrix in a sense that each and every entry in this large n by n matrix corresponds to strength between the corresponding row and column nodes. That is, we're going to have the adjacency matrix that's going to have as many rows as there are nodes in this vertex set B, and then we're going to have the same as many columns as there are nodes in this vertex set. And then for each entry here, so we're going to look at the Aij, we're going to use the strength Eij there. Now the reason why I'm using a different notation instead of using E again is because later on we're going to talk, if the time permits, we're going to talk briefly about how this Eij can be non-scalar but a vector representation. So we have this adjacency matrix, and then what we're going to say is that any vector representation of a vertex should be reflective of or should be predictive of how well connected that specific node is to another node in this graph. And then this actually does sound a bit like the linear regression again, right? Instead that now the input is going to be a concatenation of the two input vectors, or in this case, two vertex vectors. And then what we want is that we want these concatenated vector to be predictive of the scalar that is real value. And then that's how we're going to resolve the linear regression. However, if you think about it, the interesting thing is that the input is not given, right? Now, before we continue, there's a question from Carol. Does it mean we want the components of VI to be uncorrelated? Nope, we don't really care about that much. We're not going to assume anything about this. All we are assuming is that we don't know what is the correct d-dimensional vector for each and every vertex. All we know is that given a pair of vectors, vertices, let's say I and j, we know the strength. And that's how we build the adjacency matrix. And then what we are assuming here is that the strength of the edge connecting two nodes must be representable by the vector representation of the vertex. And that's what we're assuming. And then at this point, we are not even going to assume that this adjacency matrix is symmetric. So what would this symmetric adjacency matrix represent or mean? That means that our graph is symmetric in a sense that the edge, each and every edge, is undirected. So given two pair of nodes, there is only one edge that is undirected, meaning that they are connected with each other with the same strength, regardless of whether we look at it from one direction or in this permuted form. Instead, we are not going to constrain ourselves to be like that. Our adjacency matrix can very well be asymmetric, meaning that going from vertex I to j may have a different strength than going from vertex j to I. So what that means is that we need to decide what is the right way to induce this strength starting from this vector representation. And in particular, we're going to say that a vector representation of each vertex vi can be separated into two vectors. And that's going to be, I'm going to use wi and zi. And then each one of them is going to be RD and then RD. Or you can also say that it's going to be RD over 2, so that the concatenation of these two vectors are going to be just like the RD above. But as you'll see, really doesn't matter that much. And we're going to see why that doesn't matter that much. And then also, this is one thing. And then second thing is that we're going to use a dot product to compute the strength from vertex representations. What does that mean? What we are saying is that the given I to J connection, so we're going to look at the edge that goes from the ith vertex to the jth vertex. The strength of the ith vertex to the jth vertex should be computable or predictable by using Wi transpose Zj. So this is what I mean by using dot product. So what we are going to do is we're going to look at the W vector of the outgoing vertex and then Z vector of the incoming vertex, and then their dot product should be predictive of the strength of the edge, the directed edge. Now, how we do that? Now we have how to compute the prediction. We know the ground truth. Then what we need to do is write down the cost function, right? So now let's write the cost function. And in order to do so, we need to decide on what kind of cost function we're going to use. And then because it's just a scalar regression, so we're doing a linear regression with the scalar. So the natural thing is to use L2 distance. And then to do so, what we mean is that the given an edge that goes from I to J, so we're looking at a directed edge, we have the strength Eij, or equivalently, we can write it as Aij. Oops, I'm sorry. As the Aij, right? This is from the adjacency matrix. And then we want this to be as similar as possible to Wi transpose Zj. And then what would be the natural thing? We use the L2 distance. And then what it means is that we're going to simply look at the squared distance. And then what do we want? We not only want it for a single example, but we want it for all n many examples, right? And then when we say n many examples, in this case of the graph input, we have the n squared number of examples because we need to consider every possible combination. And because we're not going to assume the symmetricity of the edges in this graph, we really need to look at all possible n squared combinations. What that means is that we need to rewrite this whole thing as n going from 1 to n, and then n prime going from 1 to n. Oops, I'm sorry. We have the e. Let's use I and j. I think that's going to be clearer, right? So I going from 1 to large n, j going from 1 to n again, and then we look at Eij minus Wi transpose Zj n squared. And it turned out this is same as computing. So now A is the adjacency matrix from above, right? So adjacency matrix was constructed using all these Eij's that are the strength minus W transpose Z. And then it's going to be squared for Venn-Diagonal. And then what are these W's and Z's, right? So we know what this adjacency matrix is, but what are these W's and Z's? Is that the W is going to, oops, let's move it here. So where W is going to be W1, W2, all the way to Wn. So it's going to be a matrix where we concatenated all these W column vectors, and then there are n many of them, right? So there are n many of them. And then this is going to be R d by n. And then what we have is the Z, the code matrix, which is going to be Z1, Z2, all the way to Zn, just like before. And then just like the way matrix here, and then size is going to be d by n. So looking at this, you see how we ended up with the matrix factorization here, right? So if we think about this term, this is exactly the cost function of the matrix factorization we talked about. Only thing that has changed is that the A matrix, that is the input matrix, which we wrote as X earlier, has been replaced with the adjacency matrix. So instead of having a matrix that represents a set of input instances, what we now have is a matrix or an adjacency matrix that represents the relationship between input vectors. And then the relationship is given by this edge strength. And what we really want to know is this unknown vector representation of each and every node. And to do so, what we do is we want to minimize this cost function that is from the matrix factorization with respect to, just like before, the way matrix and the code matrix. And as you can guess, it wouldn't make much sense for us to have a D here to be larger than N. Why is that? We only have N many nodes, and then it just doesn't make any sense to come up with a representation of each and every node, N many vectors, to be a dimension that is larger than N. Because what is the most trivial solution we can come up with in this case is simply to use each and every row, let me see, each and every row of this adjacency matrix or each and every column of this adjacency matrix as the actual vector representation. And then that's not what we want. What we want is a compact and dense vector representation that tells us about the relationships among all these nodes in the graph. So how we actually solve this problem? It turned out that solving this problem is relatively straightforward, as we have learned earlier. We could use PCA, for instance, in order to solve this problem, where we're going to simply view this A not as the adjacency matrix, but as the input matrix X. And then we can solve this whole problem as PCA. We can also solve this problem as non-negative matrix factorization. And then that's not going to change much. All we need to ensure is that the edge strength are not given as the full real values, but only using a non-negative values. And then often, majority of the graphs that we run into in real life that we observe consist of the non-negative edges because they are sparse. What do I mean by sparse is that most of them are zero, and then only if there are some positive reinforcement between these nodes, that is, let's say you are talking to your friends on messengers or some kind of Instagram or the Snapchat or whatever you use these days, then that tells you about how strong your bonding is with your friend. But you often never get a signal about how weak or how bad, how anti-strong your bonding with your friend is. It's usually just none, right? If you hate your friend, you just stop talking to them. So in the case of the non-negative matrix factorization, you often just use your adjacency matrix as it is and run the same algorithm that we talked about last week at the lab session. And then that works beautifully. And then that's going to give you all those different community structure within this large scale sparse graph. Now, this is great. So what is it good for? Why do we want to care about it? One particular example I want to talk about is the visualization. And then we already talked a bit about the visualization in the lab session last week when we looked at the PCA and NMF. And in particular, in the case of the graph input, as we talked about, it's never trivial to visualize graphs in a low dimensional space as in two-dimensional space where we can actually put all those nodes in the space and then look at them. Why is that? Because graphs don't really have an absolute coordinate to start with. You can always move things around, move all those edges around, vertices around, and still you get the same graphs as long as connectivity patterns or the adjacency matrix doesn't change. So you can flip or permute the rows or the columns of the adjacency matrix, nothing changes, it's the same graph. That makes it challenging to visualize. However, we can now use this tool of the matrix factorization to do the graph embedding by finding out this unknown or the hidden representation of each and every vertex. And then we can simply set this D, the dimension of the representation. It is a dimension of the W's and Z's to be 2. If we set them to 2, then solving this matrix factorization problem using PCA, non-negative matrix factorization, or any other technique that you want is going to give us a 2-dimensional representation of these vectors, these vertices. And then you can simply put them on the screen, so plotting them, and then label each and every vertex with the name of the vertex, and then you're going to see that the similar vertices, whereas the similar represents the higher chance of having a strong edges present between a pair, are going to be clustered with each other. And then this Wednesday at the lab session, we're going to see how this kind of visualization can give us a better sense, or the easier way to get the better sense of what kind of structures underlies this kind of graph. Now, let's say so far we haven't really assumed that this adjacency matrix does not have any particular structure, meaning that this code is not going to be symmetric nor have a 0 diagonal entries. But what if our input is symmetric? Symmetric graphs. So if the graph is symmetric, what it means is that each and every edge in this graph is undirected. So that is with undirected edges. And then in the undirected edges, what this implies mathematically in our framework is that the EIJ, so this is the strength of the edge going from the ith node to the jth node, is going to be identical to EJI. So this is going to be identical to the strength of the edge going out of J into I. What it means is that this edge doesn't really have a direction. And in this case, what this implies is that the A, the adjacency matrix, is symmetric. Now in this symmetric case, we have to be a bit careful. If we want to simply solve A minus W transpose Z with the asymmetric, this problem can very well be solved on its own. Oops, not A, but W and Z. But this is a bit unnecessary because we know that if we have a symmetric matrix, then this kind of decomposition or the factorization of a symmetric matrix into the product of two matrices should be the product of the same matrix, just that the one on the left side is going to be transposed. What it means is that what we want to now solve with this symmetric matrix is this problem. Z transpose Z. So in other words, now if the A matrix is symmetric, then each and every vertex is going to have a single representation that is the Z vector or the code vector. Now before, when A was not symmetric, was asymmetric, or when we didn't know that A was symmetric, then we had to give 2 vector representations. So that is Wi and then Zj for each and every vertex in this graph. Why do we need 2 vectors? Because we need to consider 2 cases for each vertex given an edge. That is, whether this vertex is the outgoing or is incoming, given this edge. And then we need to use a 2 separate vector to represent whether it's outgoing or incoming. However, in the case of symmetric graph, what we have is that there's no such distinction for each vertex, whether it's outgoing or incoming. It's all the same thing. So that's why all we need is a single code vector Z associated with a single vector, single vertex. And then that actually allows us to solve a simpler problem with, excuse me, with the constraint automatically implemented. So when you have a graph, and then if you know that it's symmetric, the problem that you want to solve is not this one. This is not the problem that you want to solve. The problem that you want to solve is this problem where you assign only a single vector to each vertex. Okay, makes sense, right? So now you know how to embed or extract the vector representation of each node in a graph without knowing what each and every vertex corresponds to. What we have learned is that all we need to know is the relationship between these nodes. And then now, let's just conceptually, so we're not going to talk about it mathematically too deeply in this case, but let's say conceptually that this edge matrix, edge strength is not a scalar, but a multi-dimensional strength. That is, it's going to be d prime dimension. And then you can imagine that happening quite a bit. So how would you actually get that kind of thing? So let's say I want to build a social network of a school or the university. And then what I realize is that they take a pair of employees at the university, their relationship can be very complicated. Maybe they are friends personally, but maybe professionally, one of them reports to the other. So there are many different aspects of the relationships between a pair of nodes that may require different way to describe their strength. So now we're getting into multi-dimensional relationship. Oops. Relationship graph. And then this says a lot about it. It kind of makes sense. However, it's really not that different from what we learned. Simply saying that the EIJ can be R T prime. And then this multi-dimensionality comes from having this D prime many possible values that represent the strength of the different relationship that exists between the pair of ith and jth node. So in this case, how will we actually solve this problem? Let's for now assume that it's symmetric, meaning that EIJ is EJI as well. And then we know that if D prime was just 1, we know this is a problem we want to solve. Now that we have D prime many, that is larger than 1, many strength per edge, what do we do? It turned out that the one very straightforward way to do so is to solve this problem D prime many times. So for each possible relationship there is, we're going to have a separate vector representation of V. And then that could make sense, right? So what would that corresponds to is that is trying to minimize Z, but there will be as many Z as there are the different types of the relationships. And then we're going to go over some, let's say K going from 1 to D prime, and then solve this case AK minus ZK transpose ZK F squared, where AK is the adjacency matrix built using EIJ K. Because EIJ is a vector, so we're going to look at only the kth dimension and then build this, and then we can solve this. But this looks a bit less satisfying, right? The reason why it's less satisfying is that we are not exploiting the fact that these relationships must have some correlation across them. What it means is that if I am a friend with another node, then even for the professional relationship, there is a very good chance that I'm going to report to that person or that person reports to me, because I very likely won't work for or work with people who have a very low chance of becoming friends with me. So what it means is that there are some relationship among them. So then what can we do? Perhaps what we want is that we want to give a single vector to a single vertex, but we want to transform this vertex into this vector into a slightly different vector for each representation separately. What it means is that looking at this, what we are saying is that the vertex I is represented with the zi1, zi2, all the way to zi d prime, right? So we have d prime many vectors that represent what this vertex I is. But what we want is that if we want to tie them together. How we tie them together, we actually learned how to tie them together. And it's just like running the matrix factorization once more, right? What it means is that we have all these zi's, and then I'm going to rewrite this into saying that I have zi1, and then I'm going to just concatenate them, 2, and then zit prime. So this is going to be my code matrix for the ith vertex. And then what I want to do is I want to write it down as the wi transpose zi, where the zi is going to be our d-dimensional vector that tells us about this node vi directly. And then this wi is going to be a matrix, right? This wi is going to be a matrix that tells us about each and every dimensions. In fact, I'm going to this W is going to tell me about each and every relationship. And then what this is going to correspond to is W1, W2, and then all the way to WD prime. And then what it means is that this is going to be D by D prime. So what it means is that we are still going to represent the ith vertex using d prime many vectors, right? zi1, zi2, and then each vector tells us about this ith vertex in the context of one of the relationship, one of the d prime many relationships. However, what we want is that we want to model these vectors as arising from a single vector representation of the vertex. That is zi here. But then how do we get all these d prime many vectors from a single vector notation zi? Is to multiply this zi with a Wayne matrix W that is of size d by d prime. And then we can now rewrite this whole thing, whole cost function, into minimizing this equation that is going from k1 to d prime. And we're going to look at AK, the adjacency matrix, the kth adjacency matrix arising from the kth relation out of the d prime many relationship, minus zk transpose zk squared for Frobenius norm. However, let's just remove the minimum. How we are actually writing this down is that the k1 to d prime ak minus z, so this is a single code vector. Oops, this is just a single code matrix, right? We have only one code matrix now, times w, now where the w transpose, w comes from this Wayne matrix you see here that tries to get us or to transform the vector representation of each node for each and every possible relationship that we are trying to measure. And then transpose the same thing, WT, Z, and then Frobenius norm, squared Frobenius norm. Now we can solve for this problem. Wait, hold on. I'm sorry, so there is some mistake here. Let me actually rewrite this. And then the Wayne matrix, the part of the Wayne matrix that we want to use for each relationship is a single column. So we take WK, so that's going to be one of the columns in the Wayne matrix, transpose Z, right? And then transpose of that multiply with the WK transpose Z and squared Frobenius norm. So this is identical to the original form, except that these ZK Wayne matrices are reparametrized to share a single Z, the code matrix, multiplied with the dimension or the relationship specific weight vector WK. And then now we can solve this problem with respect to a single code matrix and a d prime many weight vectors, which corresponds to having a single Wayne matrix. And then suddenly what we get is a single vector representation of each vertex that encodes all the information about d prime many relationships that are available. So what it means is that it's exactly same as the problem that we solved above, where the edge strength was given as a scalar. All we do is to simply solve the same problem d prime many times, however, while sharing the code matrix. Now, before we continue, there is a question. Could you explain again what the volumes of W represent? Okay, volumes. So columns. So the columns of the Wayne matrix corresponds to a vector, weight vector, that turns the Zi. Wait, I'm sorry, I'm being a bit confused here. Oops, this is my bad. Okay. I'm sorry. I got completely confused. Let me just rewrite this a bit. I'm sorry, yes. This happens when you're trying to write down the whole thing too quickly. Let me see. So what we are going to do here, so let's back up a bit, is that we are going to represent each Zi K as the WK transpose times the Zi, where the WK is going to be R d by d prime. Now, so what this WK, which is a matrix, I'm sorry, I should have been the matrix from the beginning, just I got confused a bit, is a d by d prime matrix. This WK matrix transforms this Zi, that is a d-dimensional matrix, into, yes, I'm sorry, that should be, so this WK is a d by d matrix that's going to transform the Zi matrix, that is the d-dimensional matrix of the vector. So this is going to be vector specific, no vertex specific. I'm sorry, I'm just messing up too much. So this is vertex specific. So we have a vertex specific vector Zi, and then that Zi is transformed into a vertex relationship specific vector Zik using the WK matrix that is d by d. And then what we do is here, instead of individually or the treating Zk, this matrix, as independent from all the others, we try to model this Zk as the Z, a single code matrix, times the WK transpose, as here. And then we try to estimate both Z as well as WK transpose. And then now we get a single vector representation that is specific to each vertex. And then this vector can be turned into a vector representation that is specific to the combination of the vertex and the relationship. There are d prime many relationships by multiplying the original vector with this relation specific Wayne matrix WK. And then now we can solve this problem, and then we get a multi-dimensional relationship graph that can be represented or projected into a single space. And then we can use this to visualize a very complicated graph. So there's a question of by John, what is the dimensionality of VI? VI is just a vertex. There's no dimensionality that is specific. And we use Zi to represent the vertex I that is VI. So Zi is a representation of the Vi, where Zi is the D dimension. And then the follow-up question by Rich is, so W is a 3D tensor and each WK is a matrix. That's one way to look at it. You can just look at it from the, we have D prime many matrices. And each matrix is represented as WK, and then the WK is D by D. We're not going to go into the higher order tensors in this course, unfortunately. That does require quite a bit of the mathematical manipulation there. Okay, so this is how we're going to embed all these graphs into a low dimensional space, or to infer the vectors of the vertices. And then that allows us to easily manipulate these graphs or visualize these graphs. So, okay, this is good. And then this is the very important concept behind many of the techniques where machine learning has been successful at, especially in natural language processing. All right, so we do have now about 20 minutes, and then we're going to change the gear. So we have finished talking about how to use matrix factorization for graphs. But then we're now going to go back to our IID setting, where we are assuming that we're going to be given a data set that consists of n many vectors that were sampled from the same distribution. And then they were sampled independently from each other. Now, one thing you notice, if you think about it from a very high level point of view, is that the matrix factorization does look very, very similar to linear regression. Let's try to write a linear regression. In linear regression, we had a d-dimensional input, and then I'm going to use this kind of pictorial representation here. And then we had d prime dimensional output. So it was a linear regression, and then how each dimension of the output was computed was by computing the weighted sum of all the input dimensions. And then what were the weights? Weights were given by our weight matrix. So let's write it down once more in an equation. So if I wanted to compute the value of the jth dimension of the output, so let's say jth dimension of the output, let's try to write it down. If I wanted to compute the jth dimension of the output, then this could be written down as the sum over I, where I corresponds to the input dimensions, then Wij times xi, where xi corresponds to each dimension of the input. And then this intermediate variable, Wij, were just one of the values from the weight matrix. So this is a linear regression that we have written down. And then if we wanted to compute the entire vector output, that is the d prime dimension from the input, then we could write down equivalently as y equals just w transpose x. We're just assuming that the bias is set to 0 for now. That's easy to do now. We know how to do that, right? We're going to simply center the output matrix or the output vectors. Now, this was a linear regression. And then I'm going to draw the very same thing, but I'm going to simply use a different notations here. So we have d-dimensional input, and then we're going to have, let's use the d prime dimensional input, and then we have d-dimensional input, and then for each and every one of the output dimension in the output, the dimension is computed as the weighted sum of the input. And here, instead of using y, I'm going to use x hat. So xi hat j, and I'm going to use I as well. So x hat I, which corresponds to one of the output dimensions, is computed as, let's say I go for j, w, let me see, what is it? Ji, and then zj. And then here, z corresponds to the input here. So zj is going to be one of the dimensions in the input. And then what you see is that I can rewrite this whole thing as equivalent as x hat that is a matrix is W. Let me see. Do I want it to be transposed? Yes, I want it to be transposed. So what I want is, in fact, I want to write it as Ji and then Ij. Yes. It's going to be transposed Z, where Z was a code matrix. And then what you see is that this X hat equals WTZ is essentially the output from our matrix factorization, because our goal was to make the difference between X and W transpose Z to be as small as possible. In linear regression, as well as a logistic regression, the goal was to minimize the difference between the ground truth output Y and then what is being computed by our machine. That is a W transpose X plus bias, where the bias is assumed to be 0. And then you do see a stark similarity between these two. And then we talked about this earlier as well when we talked about the PCA and non-negative matrix factorization. Now then, what this is telling us is that we should be able to make a non-linear version of the matrix factorization as well. So how did we turn this kind of linear classifier or the linear regression model into a non-linear function? And then the idea was, in fact, if we put it into this kind of graphical illustration, very straightforward. Now remember, recall how we derived the RBF kernel or the RBF network was to introduce a set of basis vectors. And then once we have the basis vectors, we want to compute how similar our input is to each and every basis vectors. And then the similarity involved computing some kind of dot product or some kind of linear combination between the basis vector and the input. And then we apply a nonlinear function on top of that. In the case of original radial basis function network, we use the exponentiated square difference between input and the basis vector, but we talked about briefly how we can actually use any kind of nonlinear function. And if we write it or draw this in a more graphically, then what we end up with is this kind of very interesting graph. That is, we have d-dimensional input, and then this d-dimensional input is going to go into some k-dimensional space, where the k corresponds to the number of basis vectors. And then how we compute the output of each basis vector is to use some kind of weighted sum of the input vector or the input values followed by some nonlinearity. So what do I mean by that? Is that let's look at what is computed here. And then we are going to assume that we use the radial basis function. Then what is computed there, this is going to be, let's say, J in this is going to be Wi minus, Xi minus Wj, where J is now a matrix, a vector. And then we're going to look at the difference, negate it, and then compute the exponential function. And then this is going to be output from the intermediate layer, which I'm going to use as the Hj. And then once I have this, what this layer represents is how we can turn this input in a nonlinear way so that the linear regression or the logistic regression or any kind of classifier that can solve the linearly separable problem can solve the problem. What it means is that after this, we have a layer that outputs the final d prime dimensional vector. And then how this d prime dimensional vector is computed is by looking at the Wayne matrix transpose times the output from this intermediate so-called hidden layer. So this is how we could turn any linear models, including linear regression, logistic regression, support vector machines, or the softmax classifiers into a nonlinear classifiers that can solve the problems that are not necessarily linearly separable. Now, there's one question before I move on. So the question is, if the reconstruction dimension is greater than the input dimension, why don't we learn W as identity matrix in order to minimize the reconstruction error? That's precisely the point that we made. We talked about at the very beginning of the matrix factorization, is that we have to put some kind of constraints in either the weight matrix or in the code matrix, or both of them, in order to avoid this trivial or the degenerate case that does not help us understand the underlying structure of the model when we solve this matrix factorization. And one of them, and most of the constraints are there in order to avoid learning an identity weight matrix. So this is how we actually could extend the linear supervised machines into a nonlinear machines. And then now you start thinking about, can we do the same thing with the matrix factorization or the unsupervised learning? That is, we want to turn this procedure also into a nonlinear version. And then what you see is that since these two, linear regression and matrix factorization, looked identical, the same approach to extending it into a nonlinear model should apply. That is, we are going to start with RD prime code vector, and then this code vector is going to be transformed using one of these nonlinear functions. And then now here, I'm going to say I have the RK dimension thing. And then given this transformed RK or the K dimensional vector, we can now finally reconstruct the actual input, that is the RD. Now, in order to stay as general as possible, what we're going to say is that the X hat J, no, I use I there. I is going to be, it's still a weighted sum, right? So it is going to be a weighted sum, but over the K dimensions. So WK transpose, oops, WKI time, wait, hold on, let me see the rows and columns. So I should actually write it as, I'm going to write it as IK times the HK, right? When HK corresponds to, what does the HK corresponds to? HK is going to correspond to one of the dimensions in this intermediate thing. And then how I can write it down further is to go from K, WIK, where the HK is going to be some kind of nonlinear function. I'm going to say sigmoid function. We learned about the sigmoid function when we talked about the logistic regression at the very beginning of this course. Sigmoid function which follows the dot product between the input and the associated weight vector. That is, I'm going to use WK, oops, the W, UK transpose X, where UK is going to now be the weight representing the connection between the input layer, that is input vector, and the intermediate hidden layer, while W is to represent the weight between this intermediate hidden layer and the output. And then what this is telling us is that what was the representation or the code vectors we could get from PCA or non-negative matrix factorization is that those code vectors must be a linear transformation of the input, or it's a vice versa, because what we did was that our loss function for matrix factorization imply that the input vector, each input vector must be reconstructible, or they could be reconstructed as the linear combination of the code vector, or the linear transform of the code vector. But now here, what we are saying is that that's not true anymore. We should be able to get a code vector that can reconstruct the input vector using some kind of nonlinear function. Now, there is an issue with this approach, is that earlier we talked about putting the constraints in order to avoid the trivial solutions. And then there was a very timely question asking about the weight matrix becoming an identity matrix. And then that is one of the most trivial solution, or perhaps the most important trivial solution that we had to avoid with the original matrix factorization. However, with this kind of linear function, or the linear matrix factorization, nonlinear matrix factorization, we have to avoid much more trivial solutions, because it's not only the identity matrix, W being identity matrix, this mapping could also become identity function. And then there are so many different ways in which this nonlinear function can model identity function. What it means is that we have to do so much more in order to ensure that this nonlinear function is going to learn some kind of weird identity function right away. And then there are infinitely many possible ways in which that can happen that we need to avoid. So how to do that requires a bit more thinking, but that is slightly out of the scope of this course. And if you want to know a bit more about it, you can leave the question on Campus Wire. I'm going to point you to some of the papers. And then one of the most important ways to avoid this kind of identity matrix is to ensure that the norms of this weight matrix or the weight vectors do not grow too rapidly. And that's it for today. On Wednesday, you're going to look at how the graph embedding works. And then if the time permits on Wednesday, which I don't believe we will have enough time to, the Ilya or Katrina, the teaching assistants, might be able to show you what it means to have this kind of nonlinear matrix factorization. And next week, we're going to move back to k-means clustering. So we're kind of going back and forth, and then trying to introduce, just like what we did with the Bayesian linear regression, the probabilistic version of the k-means clustering that gives us the idea of how, or what is the right way to score the k-means clustering so that we can in fact choose the correct number of k, that is the number of clusters automatically. And then that's it for today. If you have any questions, leave the questions on the Campus Wire. And then I'm going to upload the video recordings as well as the lecture note as soon as the recording is processed on the Zoom cloud. And that's it for today. Class dismissed. I'll see you on Wednesday and next week on Monday. Bye-bye.